Good morning, everyone. Thanks for joining us. My name is Guy Davidson. I'm the coding manager. That's me at Creative Assembly. This is Duygu Cakmak, one of our AI programmers on the Total War PC game franchise. Now, normally I talk about the committee or 2D graphics, pushing pixels around screens, that kind of thing. But today, I'd like to talk to you, as would Duygu, about the AI involved in providing the campaign portion of a Total War game and providing an AI opponent to play against. We'll be presenting 5 sections, 2 by me, 3 by Duygu. And the first thing to do is to summarize what the Total War campaign actually is, what a turn sequence looks like, and what the win conditions are. But before we start, yes, there we are. So here's the game in action. We've got a big landscape. We've got stuff going on everywhere. It's a very busy screen. It's quite hard for me to provide a narrative, really. So this is a kind of a 2D overview of the map. You can see lots of castles which represent settlements. You've got people wandering around as they try and take control of various settlements and move things around the map. You can recruit people to form armies. There we are. You've got views of the cities and the resources that are available in them. The mission has just been awarded there to give you something to do to move you through the game. It's quite pretty, isn't it? It's quite pretty, isn't it? Thank you. Good. Quite a lot of hours went into making it this pretty. Thank you, thank you. More praise, more. I didn't do any of the graphics programming. Yes, now there's an army full of units that will go into battle. It looks like they're about to take over that settlement there. Oh, looks like a magical figure, doesn't it?
It's Russell.
It's Russell, it is. It's either Russell or David Bowie. Excellent. Stealing technology. I think he was a spy. And then we end the turn. There is actually a soundtrack. Unfortunately, Claire of Assisi was unkind to us, the patron saint of television, and we don't have sound, so I'm going to have to either whistle the Game of Thrones theme, or we could stand here in embarrassed silence for a few more seconds whilst we work out what's going on. There we are, navigating around. Okay, that's the end of that. Anyone played Risk? Oh, good. Oh, that's a relief. Anyone played a PC game? Even better. All right. You recognize some of these mechanisms. Total War takes place in a world populated by many factions with competing desires. And at its simplest, the purpose of the game is to control territory. Because if you control territory, then you control the resources derived from that territory. So those resources could be mineral or agricultural. There are manufacturing resources for building machines of war. There's human resources. So that might include a military. So that'd be garrisons or a population to recruit from. There's intellectual resources, which are driven towards the development of better technologies to build better machines of war. Diplomatic resources for brokering alliances, trade deals, and terms of peace. Sometimes you might just want to surrender. There's espionage resources. So the subterfuge plays an important part, stealing technology, as we saw at the end. And of course, tax-raising resources for funding this whole circus. Okay, so these resources all operate. Hello, what's going on here? Right, these resources all operate within an economy of opportunity cost. So cultivating one form of growth over another will carry risks with it. If you decide to go all out for recruiting military, then you may be beaten by superior diplomacy or espionage. If you put your faith in technology, then you may be overrun by axe-wielding hordes whilst you're waiting to build the better mousetrap. This is a rock, paper, scissors kind of thing going on, but on considerably more than 3 dimensions. Now, a typical turn sequence will involve inspecting all your resources, and this is what was going on. He was clicking on various bits of the map to see what his resources were, and steering them a little. You generally start with a single city and 1 or 2 armies. And you can check the properties of a city, So you can make changes to them. So you could raise the taxation rate, always popular, request construction of buildings such as a library or a training field or factories or things like that. And these resources are stationary. This is important because if you lose control of your city, then you lose those resources and all the investment that you've put into them. Because building these things isn't free. It takes money, it takes people, it takes time. Once you've worked your way through your stationary resources, you can look at your mobile resources. That's made up of armies and agents. Now, these are mobile, so your main task is putting them in the best possible place. You might choose to put armies in defensive positions around cities. This softens up other armies who are coming to attack you. You might decide to operate a more expansionist policy and send your army or armies to besiege other cities and ultimately take control of those resources. And you can merge armies with agents. So this affords your agents some protection because they're looking after your army. Or you can send agents to infiltrate enemy armies to sow discord and foment mutiny. Very effective, very cheap. So once you've completed your turn, you hit the end turn button, and then you let the other factions make their decisions. The seasons turn, the years advance. We wait for the AI to do its thing. At any point in a turn, an army might come into contact with one of your cities or one of your armies and decide to launch an attack. So there's a whole other presentation about how the battles are won. You might have seen this taking place, great sweeping landscapes of war, lots of magical creatures flying around, lots of death, carnage, blades, blood, destruction, that sort of thing. This is not that presentation. This is the campaign. This is the buy the game. It's that simple. We're just going to talk about the campaign rather than individual episodes of combat. It's all one big piece of combat, really. Other things that might happen, a diplomat might offer you a treaty, or a spy may steal some technology, again, as you saw. And that's the turn sequence. But what's the point? What's the win condition? When does play actually cease? So one of the features of Total War that's very well received by our players is that there are many hours of play to be squeezed out of a game. There are several ways to win a game of Total War. Win conditions can be assigned at the start of the game. Achieving each kind of victory can take upwards of 300 hours. And certainly you should expect to put 30 hours into completing and winning your first campaign. So let's look at some of the win conditions. Controlling a quantity of territories, that's one win condition. Controlling the entire map would be ludicrous. I mean, it can be done, but once you're about 2/3 of the way through, it's just a case of steamrolling through and hitting end turn a billion times until you win. So we don't have a world domination win condition. But simply having sufficient military might and territorial control is enough to make you the victor. Controlling particular territories is another condition. So, you might need to control all the coastal territories to win. This is what the Roman Empire did at its peak. It controlled all of the Mediterranean territories, creating extraordinary trade superiority. Subjugating or eliminating other factions is very hard work. It might be that a state of war exists between your starting faction and a few others. And so an appropriate win condition would be that you have to eliminate all of these factions, or maybe make peace with them, but probably eliminate them, because that's what we're like. And it's a case of last man standing for victory. And then there's the simple idea of forming alliances with all the factions, being the great peacemaker. And this demands, obviously, considerable diplomatic skill and expertise, but not so much military might. And there are quite a lot of feasible win conditions in general, which lead to greatly varied play styles. And this means that there are two things we need to provide for our users. A working model of the world and an AI opponent for each faction. Now, the model of the world requires, and this is, we're into programming now, so just to make this clear, the model of the world requires two different kinds of data, position and scalar data. So the position data is attached to resources like the cities and the armies, while the scalar data represents the quantities like army strength, technological development of a city, the number of buildings, the population, the tax rates, the range of effect of any particular buff that's been applied to a resource. The model is resolved over time and at quite coarse resolution. It's not resolving whilst you're watching it making decisions. It's a turn-based game. But the model is updated once per turn, and the resolution of the model takes place one faction at a time. So we'll go through faction by faction and then resource by resource within each faction to decide what to do. So the first thing that we need to achieve is a timely resolution of the model. And this becomes problematic as the game proceeds because the game starts quite small, but as the game goes on, more and more resources are created, which means more time needs to be devoted to working out how they interact and what the best thing to do is. In fact, all the armies and the buildings, it can easily double in size. And this means that the number of things to update increases, the time taken to fully resolve everything increases quadratically with each additional resource. And the next thing we have to worry about is perfect information. So in other game-playing AI, which solve problems like chess or Go, all the information is available to you on the board straight away. You can look at it, you can say, I know everything. So all the information is available on immediate inspection, but more trickier games like poker. So here, the game relies on each player being privileged to a particular piece of information, in the case of poker, their own cards. And the game has to infer the player's motivations from the information presented to it, which is typically betting habits, or if you're playing Texas Hold'em, additional cards that are given to the table. Total War falls into this final category, but there is an additional constraint. It needs to be fun. Yes, well may you laugh. That's the hard bit. The full model is, of course, the entire model of the world is theoretically available to the AI. But that would be no fun if a player went to considerable effort to create a well-manned and well-hidden ambush, and the AI carefully wove its way around it in a very peculiar and obvious way, then the player would feel cheated. It would be no fun. But above all, though, the player needs to be credible. Sometimes it needs to seem lucky. Possibly not that lucky, but sometimes it needs to seem lucky, or unlucky, or to make good or poor decisions. So the first thing we need to expose then is the information that is available to other players. So the AI needs to know what the other players know, or the kind of things that the other players know. So for example, at the start of a campaign, you can see the general outline of the landscape that you're playing on, the coast, the coast and the sort of a rough view of the terrain. And you have detailed information available to you about the area around your towns and armies. So if an enemy army comes sort of within range of your area of influence, you'll know about that. But beyond that, you know nothing. This is called the shroud, or the fog of war. And this is what needs to be available to the AI opponents, and no more. Otherwise, it's cheating. So the AI only knows what you know, only what's displayed on the screen to you. That's the information the AI has. And the next thing to make available to the AI is the same set of controls that the human player has. It would be simplicity itself to allow the AI to simply teleport armies. Oh, there, that's good. Right, you there, straight away, under the cover of the shroud, because we can't see things, we don't know what the AI is doing. That would be cheating, of course. The player would become suspicious, and actually one way of finding bugs is spotting this kind of suspicious, how on earth did they do that behavior? So next we have to motivate the AI. So given the inputs and the state of the campaign and the available outputs, the control that can be exercised over the campaign, we need to provide goals for the AI to achieve. The AI's job is to survive and to continue to challenge the player by growing, fortifying, consolidating. And that's a very big goal. It's a very big spoonful of elephant to eat in one gulp. So what we do is we create a series of goals in response to a changing campaign with the hope that we can drift the AI towards victory, which would be defeating the human player. So the AI now has inputs, outputs, and motivations. So the final thing to do is to reflect the personality of each faction. One AI is not enough. The AIs need to be different. They need to vary. Some of the style emerges as a property of the resources available to it, to the faction that the AI is steering. For example, if an AI has lots of coastal regions, it may be less bellicose, less warlike, and more prone to seeking trade alliances and improving trade routes. That's the smart thing to do. That's making the best use of their resources. But alternatively, if an AI has few resources but a fecund and angry population, it might decide that its goals can be achieved by sacrificing some of that population to battle in the pursuit of expansion. Sound familiar? Nonetheless, that isn't generally enough to create the impression of an AI personality, other things that we can do, we can just simply make decisions. We say, right, this is a fighty bunch. We've got a range of options here, but you know what, they're always up for a fight, so they're going to fight. You know, we can just decide factions are quite fighty and bias things to reflect, you know, those kinds of characteristics. So that sets the scene for our AI efforts. We've got inputs, outputs, motives, and a personality to add flavour. So, as remarked, the game is very complex. We have a limited amount of time to speak, so Duygu is going to focus on some particular aspects of the AI decision-making.
Thank you. Is this working? Yes, I think.
Good.
Oh, thank you. Hello. Before I start, I need to acknowledge the efforts of the rest of the team. Dr. Tim Gosling has been working on the campaign AI for many years and leads our campaign AI team. And Piotr Andruskiewicz is also a long-serving member of the team and has contributed many systems to the effort. Without them, we would have no game and I would have nothing to present, so thank you both. So let's start. As Guy mentioned, there are a lot of elements in Total War campaign, and the AI needs to make a lot of decisions in a lot of domains on those elements. Given the number of decisions that an AI agent needs to make, we have a massive search space, and we have serious time constraints. In addition, within each domain, the problems that we are trying to solve is different to each other. For example, in one domain, it might be a decision problem, whereas in the other, it might be an optimization problem. So with this multidimensional search and different type of problems to solve, it is infeasible to find a good set of solutions with one system and with one approach. So our approach to deal with this massive search space is to divide and conquer. We divide this problem into smaller decision domains and solve these problems within each of these decision domains. For each of those domains, we have developed different systems with different algorithms and approaches to find the most fun and challenging solution. Sorry. We have a number of AI subsystems. This number varies depending on the product as we add or remove features along the way. These ones on the slide are the main and most important ones that are common in many of our games. These AI subsystems are in charge of making all the decisions in a turn by utilizing the world state. All these subsystems are indirectly controlled by the financial system, as the financial system is responsible for determining how much budget each of these subsystems will receive. This high-level control ensures that all of those subsystems steers in the sort of the same direction. To save time and give our systems more time to find solutions, we have made a lot of optimizations in many places. Among those many places, one of them worth noting is how we maintain the world state, as all the other subsystems depend on it. So I'll talk about how we do decisions in these different subsystems, but first I want to tell you a bit more about how we maintain the world state. In order to develop an accurate picture of the world, we have created a number of analyzers. These analyzers are in charge of keeping the world state up to date. Each of the AI subsystems can call upon a subset of analyzers to get a specific piece of information that they need. Let's have a quick look at the type of information that those AI subsystems would need and the analyzers would keep in track. There are a lot of different pieces of world information that is crucial to the AI decision process. You can see a few examples on the slide. For example, which buildings are available to me to build, or which factions are important to me to make decision on. Let's look at one of them in more detail. The strength of my faction versus the strength of a faction of interest is very important to many systems. For example, the task management system and the diplomacy system are two systems that are dependent on that piece of information. The task management system needs to use this information to assess the strength of the opposing army, settlement, or region with respect to own strength before making a military decision, as we wouldn't want to attack an opponent that is clearly stronger than us. The diplomacy system, on the other hand, uses this information to decide on diplomatic relations with other factions. For example, it could use this information to assess a faction that is stronger than him, and then try to persuade that faction to form an alliance with so that it could have protection over. So while the piece of information is the same that we use, it is utilized by different AI subsystems. So instead of evaluating the information locally in each system multiple times, we have the analyzer, this one. Oh, it doesn't work. Military strength analyzer. Yeah. It evaluates and stores that information so that other systems can use it. Another important thing is here, keeping this information up to date. Because this is a very computationally expensive process, we only want to update it when we need it, and only when it is out of date. In order to achieve this, we have built a general analysis mechanism that makes use of lazy evaluation. Whenever an AI system needs a piece of information related to the world state, we perform an analysis on the related relevant information by gathering and calculating its components. Then we cache the information. Then, whenever the other systems need it for the second time, this system or some other system, we check if it is still valid or invalidated by some other systems or by some world data. If it is valid, we use it directly. If it is not, we validate it again and clear the invalidation bit and use the updated information. This figure, shows how the different analyzers interact. A directed arrow shows the information flow direction. For example, faction alliance strength analysis is dependent on faction strength analysis. That means the relationship between different analyzers is not always completely independent, as some analyzers may affect the analysis that is performed or stored by other analyzers. Additionally, action performed by the player or by an AI faction also make changes in the world state, and it might invalidate some analyzers as well. Say, for whatever reason, the faction object has changed, and it might lead the other analyzers' analysis change. And this could then have a chain reaction in invalidating the other analyzers. For example, if CAI, resource mobile military strength analysis, has changed, it may cause faction strength analysis and faction alliance strength analysis to be recalculated. But we don't necessarily have to do all the calculations along the way. Here's a quick optimization. When we need to do an update on the analysis, we check the old information with the new one. If they've changed, then we pursue the analysis. If they didn't, it means that analysis actually haven't changed. So we don't need to do the recalculations for its dependent analyzers. So we keep track of such cases to minimize the number of evaluations we do to avoid any redundant work. Currently, we have 32 analyzers that are derived from analyzer base, which is derived by the analyzer. And CI analyzer is basically responsible to maintain the analysis object, to add, remove analysis, along with accessing them. Finally, here's some code. This analyzer base is a templated class. We derive our analyzers from this base. It is responsible for delivering an up-to-date analysis by determining analysis for functions. This is a class template member function to determine analysis. It is templated over the analyzed class and analysis class, and we return the analysis object we calculate. In the non-const case, if the analysis of the world state has not yet been performed, it performs a new analysis on the relevant world state information and adds it to the cache. If it exists, but it is invalidated, then it does a validation and then returns the updated information. If it exists and not invalid, it simply returns the previous analysis. Our financial system makes use of those analyzers in order to make financial decisions, such as how much money to spend to recruit new units, or how much money should I save to do a bigger construction project in the future, for example. So we said analyzers maintain a specific piece of analysis performed on the world state. They store this information in analysis objects. This is an example of an analysis object that the financial analyzer maintains. This is one of the simplest analyses we have. It doesn't have any additional functionality. It is responsible for two data in the world, the current acceptable balance and that other ridiculously long name, absolute acceptable turn-on, turn-out goings. Every analysis has its own validate function, which is used to calculate its own data. It is executed whenever we need to validate an invalid analysis. For this example, this validation recalculates the two pieces of data it is responsible for, the currently acceptable balance and absolute acceptable turn-on, turn-out goings, and then return true if it actually needed the validation, and false if it actually didn't need it. So this is how we maintain the world state, by using the analyzers. So we have talked about how we handle the vast search space. Just to summarize, we first divide the search space into smaller decision domains and build different subsystems with different approaches. As these subsystems depend on the world state, we need to maintain the world state effectively, so we build a number of analyzers to do that job. Now we're going to go into two of those subsystems in detail, namely the diplomacy system and task management system, to see how we do decisions on them. In terms of modeling geopolitical behavior in total war, it is important to understand how our diplomacy AI subsystem makes its decisions. Let me tell you about the diplomacy game mechanics a little bit first. Through diplomacy, a faction can declare war, or negotiate peace, or make trade agreements with the other factions. Its domain is very complicated, as it needs to take into account numerous things, such as how it would make my allies feel if I declare war on someone that they like, or how treacherous I would become if I break a treaty that I signed a few turns ago, or how strong am I, do I need protection, or is there a big rising power on the world that I need to unite with other factions against. Diplomacy between factions are done through deals. A deal can include positive or negative treaties, gifts, or declarations. So the problem that the diplomacy subsystem is trying to solve is to find favorable deals to offer to other factions, or accept, reject, or counteroffer the ones that I'm already offered with. If you are thinking about a standard approach to tackle this problem in a less time-constrained environment, we would use some state-of-the-art techniques to find the optimal or near-optimal solution. For example, we could use genetic algorithms to develop a population of deals, and then we would evaluate them. We then would crossover, mutate the best deals, and repeat this process until a near-optimal solution is found. Or we could use a multi-dimensional, multi-objective optimization algorithm to find the Pareto optimal deal front, and then choose a solution from there. Here it is worth noting that deal evaluation is quite expensive, as it depends on threat analysis, attitude analysis, or stance towards the others, how the outcome of the deal will affect the rest of the world, and so on. So both of those methods I mentioned may yield a near-optimal deal. However, they're both computationally intensive, and with our limited time budget, it is unfortunately unfeasible to use. Additionally, as Guy mentioned, the fun element is very important, so the optimal solution might not mean the most fun in games all the time. So given the time limitation and our intention to make the game fun, we take the approach of searching for a good enough and relevant solution. And this is how we do it. Given there are around 100 factions in the world and hundreds of combinations of deals a faction can offer to any of the other factions, it is not possible to generate and evaluate all those deals to find a good solution within them. Therefore, first we need to reduce the amount of deals we evaluate, whilst ensuring that the deals we come up with will make sense. So our general approach is to generate a number of deals, which we then prioritize, convert them to deals, because I said deals, but it should have been goals that we generated, and we evaluate the important ones and pick the best ones to offer to the other factions. Let's first have a look at how we generate the goals. We have a number of different goal generators that generate specific goals that a faction wants to achieve towards a specific target group. These are some of those examples. For example, yes, we defined a generator called declare war on factions I dislike. This generator will populate the group of factions I dislike by utilizing the direct attitude analyzer, and then generate war goals towards those factions that I dislike. Similarly, treaties with enemies of enemies will generate different treaties towards the factions that are enemies of my enemies. And additionally, it can add some other components as well, such as demand money from faction 1, which is an enemy. So let's look into the implementation of goal generation. There's one thing I would like to mention here related to our old system versus the new one. This code snippet shows our previous goal generators. When we look at this wall of text, you can see straight away that we already made it quite complicated for us to read. As you can see, all the constructors take balance analyzers and this, and invoke generate goals method with the goals and the faction. This is clearly excessive. But things usually grow like this. You start with 1 and 2, it looks pretty, it's okay to use. Then you end up having 50 of them before you know it. So here each goal generator was hard-coded, and whenever we needed a goal generator, we needed to make a coder sit and implement the class, and implement this generate goals method along with all the conditions and all the target groups that are needed to generate this goal. It was actually very expensive, as we needed a coder to make all the changes, and as you can guess, there were a lot of code duplication as well. Since then, we have chosen the data-driven approach to replace our hard-coded diplomacy system. This generic system provides more flexibility, as you can define what a generator is, what a goal is, how a generator generates the goal, how we can define which conditions that needs to be met to generate those goals, to whom the goals will be generated towards, along with all the related parameters, all we can define solely in the data. And then our system creates all of them dynamically. I need to use this more effectively. So this system provides 2 advantages. The first one, we don't need code time to add new generators. And the second one, our designers can change the generators and goals only by changing the backend data to balance the game more efficiently without the need of a coder assistance. These are some examples of our, Nope. These are some examples of our generators. The first column is the generator key, followed by the which goals it will generate, which target group it will generate those goals to when these conditions in the condition set holds. For example, for break treaties, there are different rows. It can generate different sort of treaties. If you look at the first one, break military access will be generated towards the known factions if the conditions in the military access condition set holds. A goal is linked to its treaty components like this. A goal may have a set of mandatory treaty keys and optional treaty keys. And these are used to convert a goal to a deal. So we said there are some conditions, and goals will be generated if those conditions would hold. This is how we define the conditions. For example, if you look at the first row, break military access will be generated if the proposer's strategic stance is better than friendly towards the recipient. Similarly, offer vassalage treaty will be generated, goal will be generated if the proposer is stronger than the recipient by at least 20%. Let's look at how those table values are mapped to the actual code. For each of the conditions defined in the database, we have a static factor function that takes specific parameters that are also defined in the data. This is one condition implementation example. Here, we check if a faction is stronger than the other faction by an amount specified in the data. This one. If the result returns the desired evaluation, then we say the condition holds. Similarly, for each of the target groups defined in the database, we also have a static factor function that populates the faction list in that group. This is one example of a target group. We use the neighboring faction analyzer to populate the neighbor target group. And then goals will be generated towards that faction group, for example. It's starting to get warm now. Then for each target faction, if all the conditions defined in the data for that goal is satisfied, we generate the goal and add it to the goals list, which then will be hundreds. Now, after the generators have generated a large list of goals, we still have too many to evaluate. So we need to find a way to reduce the number of goals we are going to evaluate within our time limit. To do this, we perform a prioritization. As Guy mentioned earlier, every faction in the game has its own personality. For example, a faction may value money more than the others, or another faction would be more defensive or more aggressive, and so on. Based on a faction's personality, we give base priorities to different goals, along with some additional weightings to adjust these priorities further depending on the world state. For example, we may decrease the priority if the factions in question are too far away from each other in the map, or we can increase the priority if they share a specific culture at that time. This priority value is basically an estimation on a higher granularity level of what the potential of a goal is to that faction. Now we have generated goals, and they are assigned to some priorities based on a faction's personality. Then the first thing we do is sort them based on those priority values, with the hope that the higher priority goals in the list will be the most interesting or relevant ones for that faction. So once the deals are sorted, then we evaluate each of them in priority order until we reach a small threshold. And then we filter the good enough ones and make a weighted random selection on those, and the result is the deal that we offer. Whilst this method isn't guaranteed to find the optimal solution, it generally finds a solution that is relevant, fun, makes sense to the player, and makes sense to the faction in question. Depending on the numbers that needs to be evaluated with this method, It is less computationally intensive than the standard AI approaches that we would have used. Now let's look at how we perform the evaluation of a single goal to find and filter those good enough solutions. As I mentioned earlier, a goal might have mandatory treaties or optional treaties. For example, here the goal 1 has 2 mandatory treaties and 2 optional treaties along with the evaluation value next to it. And the sum of those values, 5, is the evaluation value of the goal. If you look at how we evaluate one treaty, we use different factors. Let's look at what they mean. The first one is the stance factor. It looks at our relationship standing with other factions. We could be bitter enemies, we could be best friends forever, or somewhere in between. For example, when we evaluate a negative treaty towards the faction in question, if we are bitter enemies, this factor will contribute towards the evaluation value. Inversely, if we are good friends, this will detract from the evaluation value. Strategic factor evaluates our relative strength compared to the faction in question. Depending on the treaty component, we may also want to take into account full or partial strength of the allies we have. Diplomatic factor then looks at the near future and speculates what will happen and how the attitudes of others will change towards me as a result. Economic factor evaluates how valuable is a treaty, if it is related to some economical gain or loss. For example, it can be one-time or regular payments, or trading items, or regions, and so on. So the evaluation value is decided situationally here based on my current treasury and my emergent need for an economical boost. And the final one is the respect factor. It takes into account how reliable the faction in question is. I would be less willingly to sign a positive deal with a faction, with a treacherous faction, as I wouldn't trust they would keep their words. Each factor here has a number of different criterion types that are used to calculate the given factor. When we evaluate a treaty, we can make use one or more criterion types. When you consider all the goals and all the treaties it contains, you can easily see why it is quite important, quite computationally expensive to evaluate a goal, and has been a focus for us to optimize the search for good solutions. Similar to goal generation, we switched to a data-driven approach for the evaluation of goals as well. We define what factors are and their relations with the criterion types as follow. For example, here there's a breakdown aggression pack at the bottom table, and it uses the following criterion types to calculate its evaluation factor. As it doesn't have any economical component, it would use the economic 0 here. For each of the criterion types that are defined in the data, we have a static method in the code implementing the required evaluation functionality. That is one example. It calculates a diplomatic factor by making a speculative query about how the world would change if we break all the deals between those two factions, and returns us some float evaluation value. Whenever we want to evaluate the value of a treaty of a deal, component value function is called. It makes an evaluation of each factor of that treaty defined in the data. Then it returns the sum of the factor evaluation values. Finally, let's look at the deal evaluation factor in the next slide. It executes the deal evaluation conditions defined in the data, and if they hold, it calls the associated criteria and sums up the values calculating in all the criteria and returns the sum. The diplomacy in the game between factions is one of the most complicated systems, yet we have developed an effective system to find good deals to offer to the factions by generating goals, prioritizing them, and evaluating a subset of them. make a little show. Sorry, it's getting really warm. Thank you very much. I think I should get this one. Thank you. This will be happy here, right? Yes. The next AI system, AI challenge I would like to tell you about is how we solve the problems in the Army decision domains. It is handled by the task management system here. This system is of particular interest because we took a known AI technique and effectively applied it to a AAA game. Let me tell you a little about the dynamics first. Every faction in the game has armies, navies, and agents. The resource mobiles, as we call them, can do a number of actions, such as they can move from a region to another one, they can recruit some units, or they can attack the armies or defend some regions, and so on. So depending on what we want to achieve, we would send our armies to attack our enemies, or we could sail out our navies to find new territories to expand, or we could select a specific army and send it to a specific region to upgrade its own units. So the problem in this domain is trying to find a good combination of actions for that faction, sourcing these with the most appropriate resource mobiles we have, and making a good plan out of those actions with the best order and with the possible coordination or cooperation between the mobiles. The task management system is responsible to solve this problem whilst ensuring that it makes the player feel challenged. We already mentioned that we have a big number of factions and regions and resource mobiles that results in a vast search space. And when I actually described the problem, I talked about three problems: generating the tasks, allocating resources to them, and making a good plan for those. So given the vast search space and three different problems to solve, we have decided to break this system into three subsystems, which I will be talking about. First, let's look at how we generate the tasks. A task is an action that a resource mobile can execute. For example, raiding a region, defending a region, embedding an agent are examples of tasks. The task generation system is responsible for building a generic list of all the available tasks and takes a similar approach to the diplomacy system where it assigns priorities based on the faction personalities and adjusting them even further depending on the world state. Okay. We have a very generic and easy way to define tasks. It has defined ways of generating minimum and maximum requirements to execute the task. Then it will be used to assist the next subsystem. When we generate a task, we add different requirements to the task based on its type or which sort of resource mobiles it will be executed with or how strong they are and so on. For example, for a simple attack task towards a region, we would look at the strength of the region by adding up all the military strength of the armies in that region. Additionally, if it has a settlement, we would add up the garrison strength to it. And then, if it has some negative effects, the region, such as attrition, then we apply an additional multiplier as we expect to lose some units along the way. Finally, we add this as task requirement, which is then used by the next system to allocate resources according to those minimum and maximum requirements. Then we have task generators built upon those generic task descriptions. These are in charge of generating tasks towards a subset of targets depending on number of situations. For example, this is a task generator that generates attack towards neighboring regions. It uses a diplomatic analyzer to find who are my enemies and goes over the neighboring regions and generates a task towards neighboring regions that are owned by the enemy. The next subsystem we will be looking at is the resource allocation. Now, our task generators have created a number of tasks along with its requirements for the resource mobiles in the first system. And also, we have some resource mobiles at our disposal, like the armies, navies, and the agents. Then the problem becomes, how do we assign these resource mobiles to the generated tasks? This is where the resource allocation system comes in. It is responsible for the assignment of resource mobiles to tasks. The resource allocation system uses multi-correlate tree search algorithm to decide which resources will be allocated to which tasks. Before we go into details about how we implemented the resource allocation system, I would like to make a little detour and see what multi-correlate research is about. The goal of multi-correlate research is to find the most promising action for a given state by building a search tree that utilizes random sampling. The most common implementation uses upper confidence bound for trees, UCT, that provides a balance between exploration and exploitation. Multi-correlate research has 4 phases shown on the slide. The first one is the selection, where you go from the root node to the leaf node until you reach a leaf node, which in UCTS, this is done by considering how strong a node is in terms of wins and loses, which is the selection phase. After the selection phase, if the node is not a terminal node, you expand the node by creating one or more children nodes. And then you select this new child node or nodes. Then in the simulation phase, you perform a playout of actions from the new child node. Generally, a playout is a randomly selected action performed at each node until a terminal node is reached. Based on the result of the playout, either a win or a loss, you then update the node information from the child node back to the root node using the backpropagation. We use multi-correlate research within our resource allocation, resource coordination, and military generator. Now that we know what the multi-correlate research is about, let's see how we implemented it in our resource allocation system. How we implement the MCTS in our resource allocation is a bit different than the standard approach. In our case, we use each node to represent an action of resource fulfilling. The search tree is then built up through allocating resources to tasks until we can no longer allocate any resource to any task. We then score the branch based on the current allocated tasks and how important they are versus the failed tasks and how important they are. Because with MCTS, we can find better solutions by exploiting the current best known solution and exploring the unknown yet promising parts of the search space, it's a good fit to our resource allocation problem. In addition, we can stop the search in any time we want and still use the results. So it is great for our game's time-limited nature. The last system we will be looking at is the resource coordination system. Now that we have the tasks allocated with some resource mobiles, then the problem becomes, what is the best execution order for those tasks to make a fun game? We also don't know the things like which path is safer for the army to go from a region A to B, or if there exists a possible cooperation between the armies along the way to execute the tasks better. This is where our third subsystem, the resource coordination system, comes in. It is responsible for finding a good plan for those tasks and coordinate between. This system utilizes some other AI systems, such as pathfinders, influence maps, threat analysis to figure out a feasible plan for those tasks, along with a MCTS-based planner. Let's look at how we implemented the MCTS-based planner in our resource coordination system. First of all, we designate two types of nodes. The target nodes that can be an army or a settlement or an agent node of my own or of my opponents. And the action nodes denotes the actions that can be done execute towards their parent target node. So now when we go to build the MCTS tree, we first generate a target node, followed by actions that can be executed towards that target. For example, here we have an enemy army as a target, and we can pick an action to apply to this target. We can misdirect it by an agent 1 or attack it with an army. So using these actions and target nodes, we can now build our search tree using MCTS like this one. As you can see, we alternate between target nodes and the action nodes, and every possible path denotes a possible plan. For example, in the left most path, we can embed the agent 1 to army 01, and then we can embed the agent 2 to the army 02, and so on. First, let's look how we do one iteration in MCTS. We select the most promising node, and we expand it by building a child node. Then according to MCTS, now we need to do a playout. However, we don't. The main reason for this is the number of actions and targets. A whole playout would end up being a combinatorial explosion if we did it. Instead of spending a considerable amount of time to conduct a playout, we use an estimation of the worst case scenario. To find the worst case scenario, we have an admissible heuristic function to estimate how good we would do or how good the enemy would do. This is basically an estimate of the upper bound on how many units we would lose and a lower bound for how many units the opponent would lose. We then backpropagate the results of this estimate up to the root. MCTS is a very good fit or resource coordination, as MCTS is adapt to change. For example, when the design requires new elements, such as new targets or actions, or we need to shuffle things around, we can easily do those in MCTS. And we can easily adjust the number of iterations and nodes, and we can stop the search whenever we need, and we can still use those results easily. Even though MCTS is able to find the vast search space that is resource coordination handled, we are able to speed things up further through additional optimizations that we did. These are the optimizations that we've done. The first strategy we employ is pruning. In resource coordination, before we do anything else, we build influence maps. These maps reflect the strength relationship between objects on the map. So by utilizing the influence maps, we detect if a target is reachable by any of our armies. If it is not, then we cannot do any action towards that, so that we remove it from our search space. And then we look at the possible battles that will happen. And then we compare the strength of the opponent to our complete strength of all our armies. Then if we cannot win that battle, then there is no point of initiating that battle, so we remove that target from our search space. And then we detect the most possible unsuccessful agent actions, and we remove those targets from our search space as well. The next optimization strategy we use is subphases. This is where we get rid of some branches here. There are some actions that would result in the same world state regardless of which order they've been executed. For example, attacking a target 1 and sabotaging target 2 would have the same result as sabotaging a target 2 and attacking a target 1. To get around this duplication and reduce the number of equivalent tree pods, we produce an overarching order of nodes. We first do all the embed actions, followed by the attack actions and the agent actions and garrisoning, and finally the move. We have studied numerous search trees and found that the best way is putting the ordering in that specific way so that the actions that affect the other actions are explored closer to the root. Even within each subphase, there is still some actions that result in the same world state, regardless of their execution order. So the next strategy we employ is the node ordering. To prevent duplicate branches, we have enforced some arbitrary ordering scheme. We use unique indices for targets, and we only generate branches in increasing index order. And the last optimization technique we employ is spatial partitioning. Before we build our search tree, we can reduce the number of search space even further by analyzing the reach of the resource mobiles on the map. We put the resource mobiles into different groups if their targets are mutually exclusive and solve them as different search problems as they wouldn't be able to coordinate with each other anyways. It's not this clean and simple in the real domain, but for the sake of simplicity, let's look at this example. For example, Army 1 and Army 4 doesn't share any targets, so we can build a separate search tree for those two. Whereas Army 2 and Army 3 shares a common target, so we build another search tree for those two. Solving the problem for different groups individually for each of the search trees reduces the number of combinations and size. So we have talked about the task management system, how we use MCTS in our resource coordination and allocation systems. We find MCTS is a good fit to our problem as it is easily customizable and it gives us a good exploration and exploration trade-off, as well as it works well with our game's time-limited nature. We have also made many optimizations to direct our search space to find the solutions faster and more effectively. Thank you.
Well, this is all very lovely, but we have one quite important and serious problem, the big elephant in the room. I alluded to this in my opening remarks. Duygu alluded to this as well. And that's the problem of how long it takes to resolve the world one round at a time. There is a ton of stuff going on. Let's start with some raw numbers for the start of a campaign. There are 269 regions, each has a settlement in. There are 139 factions at turn 1. Each faction has between 1 and 3 settlements and 1 to 5 armies, and also up to 3 agents. So it looks at another way, there are 269 settlements, 300 armies, and 200 agents at the start of a campaign. Okay? Now, if we want to keep round times to 20 seconds, then we have 0.025 seconds per entity to work out what to do, to consider our options and choose the best one. So consider what we're doing. We have to find out what is within reach of what else. Ton of pathfinding there. We could cache path costs to each position from each, but we have a giant path database that we keep at the start of the game. But those costs depend on what is doing the travelling. A mounted agent is far swifter than a lumbering great army. A naval route is only viable if a boat can actually get to the port in time for the disembarking army. It might be that the land route then becomes quicker than the naval route, but there might be greater threats on the land route. They have to be costed, and those threats may also affect the provision of the boat to the port. And of course, if the port is blockaded, then these calculations come to nothing. You know, if the port is blockaded whilst we're waking away there, those calculations come to nothing, and the land route must be taken, unless the blockade signals greater tension in the region, and the risk of taking the land route is now considerably greater potentially. So, no, we can't just cache the costs. There's an awful lot of calculation going on each time. They need contextually modifying. But 0.025 seconds, that's a lot of cycles over a lot of cores, isn't it? Don't forget we've got to draw this. But we still have to worry about processor caching. That can soak up a lot of cycles. There's a lot of data all over the model. Cache coherency is extraordinarily hard. And then we have the planners, which Duygu mentioned. A game of chess has a large number of moves available. But the best move is not necessarily apparent just from the state of the board. You might want to develop your position as time goes on. And that requires planning beyond the current move. And this is where things become very time-consuming. Resource interaction search space increases quadratically with additional resources. When you add time to the calculation, then it increases a little less than cubically. It's horrible with each additional round of turns. Things balloon out. Profiling, therefore, becomes particularly important. There are plenty of tools available which will tell you how much time you're spending in what chunks of code. We use Sleepy quite a lot. It's a particular favourite. But ultimately, although we need to know which system is, which system's are proving most time-consuming as the game progresses in comparison to one another. There are many systems cooperating together. So we need to know which is the bigger, which is the smaller, rather than absolutely knowing which one is taking all the time. We have our own set of macros and functions for collecting telemetry from all the components, and this gives us quite a lot of resolution while the game is running, and we can generate a huge amount of data, and we use Chrome tracing to visualize it. Anyone here use Chrome tracing? Is it a good thing? It's a very good thing. Okay, use it. Look into it. It's made quite a difference to how we do our profiling. It's an effective front end to all of our profiling efforts, really. It's marvellous. Our visualizations, they highlight to us where the different sub-blocks are and what the round time and what the turn time looks like. We've got to a point where we can turn resolution up and down in different areas, and it does typically work quite well. We have a good idea of where the time is going. That's the important thing. Because you can't control what you can't measure. Getting ourselves to the stage where we can take accurate measurements has been a long activity over the past few years. So we have some high-level and fine-grained macros, but we also use off-the-shelf tools for those, oh, that's weird moments. These are the moments that usually precede great breakthroughs. So when weirdness happens, it's good to get as much information as possible. It could be a bug, but let's, maybe it's not. These tools in general, they've been useful for seeing how things have changed over the very long term, over years. We've been developing Total War now for, 20 years. And we can see what durations have changed and find out why, what we've done to a system to make it worse or to make it better. We keep snapshots of data over time so that we can see what parts are getting slower through the development of a project and which are getting faster, ideally all of them. We've got an extensive system of auto-testing as well. Everybody in the studio leaves their machines on overnight, and we spend the out-of-hours cycles just running the game. Time and again, exploring different scenarios, measuring what happens over hundreds of turns, hundreds of rounds of the game. How durations change over time, are they going up or down? How quickly they're changing? Are there any interesting points of inflection where suddenly there's a jump up or down in time? In Warhammer 2, there's an event called the Chaos Invasion. What happens is a faction suddenly sweeps into presence, scares everyone. It stirs things up. Things can be running along nicely and suddenly, bam, there's a pile of things that everyone has to suddenly pay attention to. It's on the radar of many factions. Each faction has to react to it. This bumps up all the timings. There's a change to the personalities of the factions. There's broad change. So one seemingly obvious solution might be to set budgets. Decide that you're going to spend between 20 and 60 seconds, increasing as the game lengthens, perhaps, and take no longer than 60 seconds at the end of the game, and simply divide the time up between the factions or the systems appropriately. So we could set a round time target depending on what kind of machine you're playing on. If you're playing on a low-end machine, then we can say, oh, it's going to be about 40 seconds. If you're playing on a really expensive high-end machine, we can say, oh, yes, 20 seconds for you, sir. And towards the end of the game, you don't want it to be creeping up harder than a minute, so there's an absolute cap. To do this, though, you'd need to set caps on the various systems, but we're not budgeting between components, but also between factions. We're budgeting in two directions. There are two pools on our constraints. How do you estimate a reasonable amount of time that an individual faction should spend within its turn? It's likely to change as other factions interfere with it. You're going through the turn and then suddenly everything's changed. All your predictions come to nothing. So we've got no solution for that, unfortunately. No, sorry, there's no. If you have, bear that in mind. We can vary the MCTS search size, and if it saturates, we can stop and take the best solution, and that's great. And early on in the game, we can get to the best solution because we don't saturate everything. We can control the upper bound that way, but we're not mediating between factions and components dynamically. We could scale the MCTS search size, based upon things like you're the biggest faction, so you're going to get all the time. But that would mean positive reinforcement, as the biggest faction would have more opportunity to get a better solution search space, giving it better opportunities to expand, remaining the biggest faction. Something that we do try is to set competition between all the components, to try and get the time down. The biggest things are the allocator and the coordinator times, as you might imagine. And the cheapest of these will swap to and fro as developments improve, so we can keep those things coming down. Diplomacy has been receiving a lot of investment recently, and we're making big changes as a result. And it's become increasingly complex because it's doing more stuff and finding better, more credible actions to take. One of the problems with diplomacy is that the human subtlety of it all is it's blindingly obvious to us, and yet so terribly hard to encode. We can't sanity check offers for apparent stupidity beyond the numbers. Cost is no indicator of value. You could take a stab at time budgets, but you don't know ahead of time whether or not they will work. That's really what we're getting at. And the other problem, of course, is we don't use MCTS, which is this wonderful thing that we can just stop and still get something useful from, for all our systems. It's not appropriate. We have different types of optimizations. We don't have a good way of cutting off, for example, building construction choices and just saying, stop, pick the best one. We could say, well, this faction doesn't get to move or build anything this turn, but the players spot it straight away. They hate it. We know they hate it. They tell us they hate it. You end up with factions that are just doing a small subset of things, and that in itself leads to weird behaviours. We tried reducing things so that factions would only construct and repair. Those are actually quite cheap things to evaluate, and not allow movement of forces or recruitments. Those are very expensive things to evaluate. And if you have 100 factions, you might get away with the minor factions being idle, but that reinforces the problems. The minor factions are the cheapest to evaluate anyway. The savings do add up, but over time you can't have factions doing nothing. You certainly can't get away with major factions idling. Particularly, we have to spend our time on the things that are most impactful, the things that people see. Coordination of armies is very valuable and obvious. Players will see armies moving through their territory. They'll see battles taking place. They'll witness the fabric of the political landscape mutating as a result of all the battles and the trade deals and the alliances and the regional conquests. If we outmaneuver someone, they get annoyed. They admire the AI that went into it, though. It seems like cunning. Artificial cunning is much more valuable than artificial intelligence. But if something silly happens, that's not so good. Walking into an ambush isn't silly. Walking into an ambush, you go, oh, ho, 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 ho. It's great. When an AI army walks into your ambush, you feel on top of the world. You really do. But walking past an enemy army that clearly outnumbers you 3-1, just striding through them with a cheery, hello, it's not a sensible play. And similarly with diplomacy, it's obvious. It's just obvious when a silly deal is proposed. We know this to be the case. It gives the player pause, though, when an interesting deal is offered. So we spend more time on those things. Things such as, there's a certain RPG element as all the various characters skill up, then you can assign skill points to them. Some of them might become a little bit brighter or a little bit stronger, a little bit more charismatic. But as far as the AI is concerned, that's really not very important. It's just a case of rolling a dice, or rolling a weighted dice, probably. But how about a little cooperation from the user? You know, perhaps they would like to be presented with a slider that affects the difficulty by increasing the strength of the AI, offering it more time to resolve the round. But not every component scales. The allocator and the coordinator could probably run for longer, but then, of course, we run into things like increasing the number of options in the search space again for even better results. And it's likely to be an unbounded problem. We'd be doing less pruning on the search space. If we had more time, we'd probably spend it on task-related areas. So there we are. We gave you a picture of the operation of the Total War campaign game, how the turn sequence works and the win conditions are established and how to equip the AI. And then we looked at the decision domains, AI subsystems and analyzers, with a closer look at the financial analyzer. And then we considered how diplomacy works, how we generate goals such as treaties, and how we prioritize them through considering evaluation factors. And then we looked at task management, how we use Monte Carlo tree search to choose the best task to generate, and resource coordination and optimization. And finally, we looked at ways of getting this all to happen in the shortest amount of time possible, demonstrating that it's not simply about getting the code to run as fast as possible, but about choosing which code to execute. One more thing. I'm very proud to work at Creative Assembly. I just joined at the end of the last century, when we were just 30 strong. Now there's over 500 of us. We've got offices in Horsham in Surrey and also in Sofia in Bulgaria. We've released some acclaimed and celebrated work. We just got nominated for a BAFTA for Warhammer 2. Besides the historical Total War games, though, as well as the Warhammer series, we've also released Alien Isolation and Halo Wars 2, excuse me, on the console platforms. So perhaps you'd like to join us. We're always on the lookout for talent, of course. And we've got openings in our new console IP for a tools programmer and for an engine programmer. There's no Unity here. It's all, there is none, is there? None at all. We have an engine programmer here, yeah. Yeah, everything's proprietary as far as possible anyway. We've also got openings in our arena product, which is a multiplayer online battle arena. We have a back-end developer. I'm not sure what one of those is. It's all just words. I don't know. I'm cold. Come on. Also, there needs an engine programmer. I do know what one of those is. And of course, we've got openings on our main products. We need a tools programmer on our Total War products. We have an engine programmer opening. And actually, we have a campaign AI programmer opening. So, you've seen what it's like if after seeing all this, you think, if you'd enjoy the challenge of developing the next generation of Total War games, that's really what I'm saying. It's fabulous. Do contact us. We'll see what happens. Any questions?